Hello everyone, welcome to my channel. Now in this video I'm going to discuss the topic of first law of thermodynamics and then we will see the Mayer's relation. Now first law of thermodynamics actually basically it relates heat, work and internal energy. Okay, so it is a relation between how this heat can be converted into work and what is the change in the internal energy. Now before we go into the details of this law, first we need to understand a bit about the term internal energy. Now this is denoted by the symbol capital U. Now internal energy, as the name suggests, it is the energy of the molecules, of the gas molecules. Okay, now this is the sum of kinetic energy and potential energy of the molecules. Internal energy is a macroscopic variable, that is its value depends on various factors like pressure, volume, temperature and all. Now it is also a state variable, that is the change in internal energy, it is independent of the path. Okay, it depends on the initial state and the final state. That means if you have a cyclic process, so in the cyclic process initial and final states will be same. So for a cyclic process the change in internal energy will be 0. Okay, so it is a state variable. Now this is also quite interesting that these quantities heat, work and internal energy, though they are related, but the change in internal energy is a state variable, that is it is path independent, but heat and work, these two terms are path dependent. Okay, now what does this first law says, that suppose you have a system. Okay, now to this system if heat is given, okay, so delta Q is the change in heat to the system. Okay, that is delta Q amount of heat is given to the system. Now a part of this heat will be utilized to increase the internal energy So delta U is the change in internal energy and the rest will be used for performing work. So delta W is the work. Okay, so now if you apply principle of conservation of energy, so this heat is responsible for increasing the internal energy and the rest is used for performing work. So I can write delta Q is equal to delta U plus delta W. Okay, so or I can write delta U is equal to delta Q minus delta W. Okay, so now in this expression, this delta Q, the change in heat, it is dependent on the path followed. Okay, similarly the work done, it is also dependent on the path. Okay, whether you are taking the process in a isothermal way or adiabatic way, those things. And but this change in internal energy, it is independent of path, it only depends on the initial state and the final state of the system. How can you change the internal energy of a system? Okay, now the general idea is, like suppose you have a closed container containing some gas. Okay, now we can supply heat to the system. Okay, so by supplying heat to the system, the internal energy of the system can be increased. Okay, now similarly if you have a suppose a cylinder fitted with a piston, movable piston. Okay, suppose this is a piston and this is some sort of cylinder containing some gas. Okay, now if I push this piston in the downward direction, if I push this piston in the downward direction, so this gas will be compressed, so that means I am doing work. So by doing work you can change the internal energy. Internal energy of a gas can be changed by two ways. One is by supplying heat or by doing work. Okay, so the mathematical form of the first law of thermodynamics, it is we have delta Q is equal to delta U plus delta W. Okay, now this delta W can be written as P delta V. Now here delta Q, in this expression delta Q represents the heat supplied to the system. Okay, this is the heat supplied to the system. This delta U is the change in internal energy of the system. Energy of the system, and delta W is the work done by the system on the surrounding. Okay, work done by system on surrounding. So if the temperature of the gas is increasing, that means that in that case delta U will be positive, that is there is an increase in internal energy of the gas. Okay, if heat is lost by the system, then delta Q will be negative. If heat is given to the system, delta Q will be positive. Okay, if work is done by the system on the surrounding, in that case delta W will be positive. If the volume of the system increases, okay, if the volume of the system increases, so in that case delta V will be positive and delta W will also be positive. Okay, so these are the sign conventions we'll be using. Now another thing is like if for a cyclic process, this delta U will be 0 for cyclic process, delta U will be 0. So in that case delta Q will be equal to delta W. Okay, that is the entire heat that is given to the system will be converted into work. So next let us see one term called the molar specific heat. It is denoted by the symbol C. Okay, now molar specific heat, it is the amount of heat required to raise the temperature of unit mole of substance through 1 unit, or mathematically it is written as C is equal to 1 by N delta Q by delta T, where N is the number of moles. Okay, so this is molar specific heat, and if this is in calorie, this is mole, and this is in Kelvin, so this will be calorie per mole per Kelvin, or you can write calorie per mole per degree Celsius. So these are the two units of molar specific heat. The molar specific heat of a gas is independent of the amount of gas. Okay, and but it depends on a few factors, like it depends on temperature, it depends on the nature of gas, and it also depends on the process through which heat is supplied. Now heat can be supplied to a gas by two processes. One is heat supplied at constant volume, the other one is heat supplied at constant pressure. So corresponding to these two processes, we have two molar specific heat of gas: molar specific heat at constant volume and molar specific heat at constant pressure. So molar specific heat at constant volume, it will be 1 by N delta Q by delta T, where V is equal to constant. Okay, that is heat is supplied keeping the volume constant. Okay, now similarly molar specific heat at constant pressure Cp, it will be 1 by N, N is the number of moles, delta Q by delta T, where P is equal to constant. So here heat is supplied, delta Q amount of heat is supplied such that delta T is the rising temperature at constant pressure. Pressure is kept constant. Okay, so now next we will, since now we have learned about two molar specific heat of gas, Cp and Cv, so next we will try to learn the relation between the Cp and Cv, that is called the Maer's relation. So next we will learn about Maer's relation. From first law of thermodynamics, we have the relation delta Q is equal to delta U plus delta W. Okay, now this delta W can be written as P delta V. Okay, now suppose heat is supplied at constant volume. Okay, so if heat is supplied at constant volume, so V is constant, so in that case this delta Q, it will be N Cv delta T. Okay, this is because just now we have defined Cv is equal to 1 by N delta Q by delta T for V is equal to constant. Okay, so from this we can write this delta Q is equal to N Cv delta T. Okay, so this is when V is kept constant. Now if when V is kept constant, this work done will be 0, because delta V, if V is constant, delta V will be 0. So in that case this quantity delta W will be 0. So I can write this delta Q is NCV delta T, so that implies delta U is equal to NCV delta T. Okay, Now suppose the gas is taken through a process in which the pressure is kept constant. So in that case, delta Q will be NCP delta T, where Cp is the molar specific heat at constant pressure. Okay, so now we have delta Q is equal to NCP delta T, and delta U we have. So now we have delta Q is equal to NCP delta T, and delta U is equal to NCV delta T. Now if you substitute these values over here, we have delta Q is NCP delta T, so this is NCP delta T. Delta U is NCV delta T, so NCV delta T. Delta Q is equal to delta U plus P delta V. Okay, so now this delta Q, it is replaced by NCP delta T. Okay, now delta U, it is replaced by NCV delta T, and this is P delta V. Okay, so now for ideal gas, PV is equal to nRT. Okay, this is the ideal gas equation. So from this I can write P delta V is equal to nR delta T. So that means this P delta V can be replaced by nR delta T. So this is NCP delta T is equal to NCV delta T plus nR delta T. Okay, so now here this N delta T, this cancels out. So we are left with Cp is equal to Cv plus R, or Cp minus Cv is equal to R. So this is called the Mayer's relation, Cp minus Cv is equal to R. Okay, now it also shows that Cp is greater than Cv, that is molar specific heat at constant pressure is greater than molar specific heat at constant volume. And what is the difference between them? It is R. Okay, R the gas constant. So we have Cp minus Cv is equal to R. Okay, so from this one observation is Cp is greater than Cv. Okay, now in later on in adiabatic process we will find that there is a term called adiabatic gas constant gamma. Now it is the ratio of Cp by Cv. Okay, so I can write Cp is equal to gamma Cv. Cp is equal to gamma Cv. Now if I substitute this value over here, it is gamma Cv minus Cv is equal to R. So if I take Cv common, it is Cv is equal to R by gamma minus 1. Okay, so this is the relation between molar specific heat at constant volume with adiabatic gas constant. This is gamma. Now if I substitute this value over here, I get Cp is equal to gamma R by gamma minus 1. Okay, so this is Cp and Cv in terms of gamma and R, and this is the Mayer's relation. And hope you find this video useful, and it helps you in understanding the concept of state variables and concept of internal energy and thermodynamics. My best wishes for your academic endeavor. Good luck.